Okay. Let me start the software. Our civil Storm V8i. Click on it. Start. We click create new project file. Okay. It's opened. Now, first of all, we have to make sure that the units are adjusted. It means the units must be in system international. Usually, when you open for the first time Bentley, then the unit comes as US customary. So you will have to change it into this and save. So as you see, these are the icons. All the icons are here, and you can choose from the drop down menus and so on. But to start a catchment or to start a project, we have to give or inform the software the geometrical data first, and then the hydrological or hydraulic data. So let us introduce our project on the geometrical files. So to build or to construct geometrical files, here are some icons. For example, here is a catchment icon. So we have to build our catchment first. So this is how to build these sub-catchments. Right click, then you see, and this is catchment 1. Then the next catchment will be like this one, like see, right click, then this is catchment 2. The third catchment, maybe, let me start here. You see, we can make the catchment as our, you see, right click, then this is the third catchment. So now we have to create the conduits, the network system, the manuals, and so on. Manuals are usually inserted in a model, in a stormwater model, where it's necessary. For example, when there is curvature, changing direction, it means, or when there is the distance usually must be if it is more than 30 meter, we have to add another manual, especially if the manuals or the SWOT system will be cleaned manually. If it is a machine, we can increase the length, I think. So to create the conduits and the manuals at the same time, we can use here the conduits. See, for example, we can put here the second manual. It automatically put the conduits. The third manual, the fourth manual, then here the outlet done. See, okay, cut here, done, and I have to morph. Okay, done. Then you see, click outlet, and I have to morph this into an outlet. So there must be always an outlet icon here to indicate that, or not only actually to indicate, but to inform to the software that is an outlet point, so that it will design according to our, it will calculate the hydrology and hydraulics based on our information. So that's it. If we were going to create another manuals, for example, here in join, you see here, click done. Another conduit here, click finished. See, like that. These are conduits and manuals. Actually, we can also we can also put. Actually, it's better to put one manual for, see, one catchment for one manhole, where the the manual gets its water from the inlet, is from the specified catchment. That means, let me show you how what I mean. You see, if this is a small catchment, you see, if this is a catchment, then it's better to put one manhole. See, one man here, a manual here, so that this anything runoff from here, any runoff from here will enter into this manhole, so that it will be easier to calculate. I think we will see in the already made project that how the network was built and so on. So that's all. This is how to build your geometrical files, and the next step will be we have to inform the software how the flow goes. You see how this geometry works. I mean, see, step by step we will inform software how to proceed, how to calculate for us. You see, this is that will be that will be shown in the next file or project that was formulated already. So this is how to create a project, so that we can save this, and save it like as project, for example, project, any name, you can give any name, project Mesfin, you can say project Mesfin. Okay, so save it. A project file always has CSD extension. So that's all. This is how to create a project. It's finished. That's just to show the steps how to create a project. So the next step will be to open an existing project and show how to validate and compute the hydrographs and so on. So let me close this one. Let's clean, close, and let me open another one, which is already I mean, it's completed. Present. Okay. Yes. This is a project which is already made. You see, as you see, for this catchment, here is the manual. So everything or the runoff from this catchment will flow to this one. From this one, from the BV do from catchment 2, it will flow here. So in the similar fashion, it goes like that. You see this is the network and so on. Then this one is the outlet. This is a branch. You see, while we are designing a storm, so maybe this one is the main storm canal. So we may design this one for a recurrence interval of 10 years and so on. But for this one, this is we design according to when and considering different scenario maybe, but let us do different scenarios, and we will see how to make scenarios and so on. So, and it's good to consider also the catchment covers catchment behaviors. You see, catchment with a forest catchment, which is covered by another grass or agricultural area or village, and so on. All these catchments should be described. So it's necessary to have the information to use to calculate the storm discharge in this software. So this is the already made geometrical file. See, now we need to specify how the software should proceed. See, so here is a flexi table. We have to click here, or we can find flexi table here. So just click here. Then this is a catchment table. On the catchment table, you see the specified names. You see, when you specify the names, it will put automatically all the catchments are placed here. You see the names. BV1. BV means bassin versant. In French, it means watershed. Watershed 1, watershed 2, watershed 3, something like that. So the there are no here the manuals. Oh, yeah, let me check here. Maybe see the software here. These are the outflow nodes. We can pick it like this. Take it here. See, this is a catchment manhole CH. You see, you can see. Let me make it bigger. You see, CH1 is the manhole. T8 or something like that is the conduits, and BV9 is the catchment. So each catchment has T or a conduit manhole. It's named, the catchment itself is named as BV9 or something. So we have to inform now catchment or bassin versant A. Let me show bassin versant A. This one is bassin versant A, or catchment watershed 1. The runoff from this catchment will flow into this manhole. That is, this one is the inlet area to this manhole. So we have to inform the software that BV1 will flow to SH1. If we don't want, if we want BV1 to flow here, so we have to click here. Then a pop-up window comes out. Then it says select from the drawing. You see, and you select this manhole. So you see, it indicates us now that BV is going to send the water to manhole 2. So manhole 2 will take or will be used as an inlet structure from catchment 1 and catchment 2. That is how we inform the software that the network, how the network works, you see, so that it will calculate for us according to the information given. So that's it. And this table, you see, the yellow columns are not editable, and only we edit the white tables, you see. So let me here volume something. This is calculated. You see, already calculated. This is area. You see, let catchment area. Let me rendering it. Okay, let it be. Yeah. See, catchment area is already given. That as I've already mentioned that we have a data that is the catchment cover, occupation du sol, bassin versant, and surface in French is this in hectare is given. The total area is 60.2 hectare, and it at actual means present state, and it at future means future state. So here there are habitants, people who are living in this village, habitants in French, English, employee 2007 employees are living in this village. So we have to calculate their daily waste in liter. You see, for example, according to there is a consideration that one habitant is going to create 180 liter per joule per day, and another the others, especially the employees, workers who are employed in industries and so on, and an industrial waste is less than the residential houses, because I think because industry waste is less, because many people using it's for domestic water and so on and so on. It's much higher in industries than in residence. So any employees we have to reduce by one third. See, that is, it means one third of the the habitant or the residentials. It produces one third of the residential waste. That's all. So the calculation goes like that. For example, 3 employees, you see, as taken as one habitant. So for 3 persons, 180 per joule or per day will be considered. So that's how this one is calculated. You see 270 pupils will be divided by 3, and they multiplied by 180, because one person create 180 liter per joule. So that's in liter per joule, and this one is in meter cube per second. So this is in the present state. Then this one is in the future state. In the future state, well, the number of population increased here. Another village is created. You see, this was agricultural pre-shamp area, um, and also this was also a pre-shamp area. See, now it already has become a, a village, you see, and the number of population people are living in that. So we have to consider a future state as well. It means considering a future state means we will um, consider the future state, but you see we are not going to design a very big structure, because if we design a big structure, then the velocity will be less than the minimum required, so that the minimum required velocity in a sewer, especially in combined sewers, is 0.770, something like that. And most of the time 1 meter per second is good, as it is a cleansing velocity. You see, it will clean um, uh, by itself. So um, so minimum velocity always has to be considered in the design process. So this is the data given, and this is the catchment. You see, this is the time of concentration. Time of concentration is the time um, to the time of arrival of the runoff from the farthest point to the point of interest. You see, for example, we can see here, here, this is an inlet area. You see, for example, for the time of concentration for um, this catchment system, for example, as the outlet, let us consider as the outlet's time of concentration is the time of arrival of the runoff from the this is the furthest manhole. You see, when this one arrives to this point, then the discharge will be, the maximum discharge. That is the time of arrival of the maximum discharge is called time of concentration. We have to calculate the time of concentration, and there is a formula to calculate the time of concentration. I can see, let me, you see, time of concentration is, there is an equation, is time of concentration in minutes. Minutes is given, you see, 76.3 under radical, area in kilometer square, divided by intensity, which is in percent. So for example, for an area, for catchment area of 4 hectare, as it is given in our data, we have to change into this one into kilometer, then it will become 48 something in kilometer square, in kilometer square. Then we will substitute this into, and I is given as 2.8%. So just substituting this into this equation, 76.3 divided area is equal to 0.0048 divided by 2.8, which is 9 point something, and divided by 16 to change into hours because it is in minutes, so it becomes 0.166. That is the how to calculate for the catchment area of 4.8. So we can calculate, it's the same as it is calculated in the same fashion. Here is a formula you can see, and every catchment, every time of concentration for each catchment is calculated in the same fashion. For pent means a slope, for a slope of 1%. So we need to put this information to, this is the area. To put the area, we just click here, we just copy and control copy, then here paste it. See, and this one was not like this before, because you see, you can see it was unit hydrograph, so you see like this. And then if you want to change into that modified, then global position, you click right click and then click global, then modified rational method, then click. You see, just right click here, global edit, click, and then it comes, this table comes, then you just click here, then choose what you want. Now the time of concentration is here, The yellows are uneditable. We only can change the same. We copied and pasted here in the notes. This is for the catchment, and that's all. These are the only information we need now. Whenever we want the headers, you see we can edit them here. You see, for example, if this headers are not available in our column, then we can put them like this. You see, so we may also create another. So that's all. This is the information required to run this model. Now the next step will be creating scenario files. You see, we need to create scenario files. So to create scenario files, we need to go to the storm data component here. We need to go to component, then storm data. You see, in the storm data, this is intensity, depths, frequency table. See, you have to create like right click here, new, another user defined intensity, depths, frequency table 3. You see, then you put add return period here, for example 20 years, and now duration, for example for 0.5 hours, duration in hours. Then we have to calculate the intensity in millimeter per hour for 20 years. Yeah, you can use this formula. You see, you can use this formula. Okay, we can use this formula, you see, to calculate the intensity. T is the return period. A plus B are these are regression equation coefficients. A is a slope and B is the other term. See, so A is calculated with this formula. C means if t greater than 17.5. The time is, if the time in minutes is greater than 17.5, we use this one, and if not, this one. So t is in minute, so you can use either or this one according to the time we have. We need to calculate. Then B is calculated, can be calculated in the same fashion. So it is in minute. So here is an example how to calculate whenever we know a return period and the minutes, the time. So here is calculated with the same fashion. We can calculate or use these questions and can calculate the intensity millimeter per hour for a quarter return period. This is some tables that we can pick already calculated. You see, that's how we calculate. That's how we calculate. Okay. What's this? Okay. That's it. So we can put here the number, for example 79 or maybe 60, maybe, yeah, according to the result. So we can say that's all. It's just done. You see, but we don't need this one to add now, so we delete it. Not necessary. So I've done for 0.5 hours or 30 minutes in 5 hours, and then 10 hours, 10 years. 10-year recurrent period and 5-year recurrent period. These are calculated according to the formula. Then you just close. Now to the scenarios. You see, you come to analysis and scenario. Then you put this. I put them in this base scenario. For example, I can create another one, new child scenario. You see, child scenario, and I can t is equal to 420 years. So you see, created. So that's how we create these scenarios. Then after that, we go to an alternate, and we create also T5, T10 years. See, these are created by just right click, child alternative, create. You see, and change the name, right click, rename. See, then you can put 20, t is equal to 20, t is equal to 20 years. Hydrology alternatives. So that's all. So now we don't need this one, delete, because Stormwater design is always only for 10 years, most maximum. That's all. So this is created now. We can see, for example, see, you can come here and arrange hydrology 5 years. Okay, and here click hydrology 10 years. You can change, you see, like this, 5 years or 10 years. So okay, all the output, inflow, rainfall, something like that will be the same. So that's all. We have created all. Now the next step is to put some fix it. I see as the information given in the data here. You see, there is one village which has an additional input into the system, that is 0.01. So we need to go to see BV3 here, 1 2 3. This one is BV3. You see BV3, and right click on it, property, then inflow here. This you see fixed load 0. How much? 0.01, and hydrograph load is, that is the minimum recorded data for Europe. You see, there is profile record for dry period seasons. You see, in dry period, this is the minimum data, and I think this is the standard. So you need 24 in a day. You see, just copy this one and then paste it here. Just Control V, paste it. So you can see the minimum daily hydrograph in a dry period. You see, during the night time there is no waste. You see, no flow. The flow reduces. During, you see, in the morning it increases again. You see, then decrease, and at 20 it increases. It reaches its peak. You see. So again, something like that. So we have to add this thing into the system. Okay, so finished. But you see here, I have already this project as because I just run it before for the future. You see, let me check. You see, yes, you see there is a fixed load in the hydrograph here. You see, we don't need this one because at the present state we don't need that one. And also at 6, you see, I have done this before, so I need to. This doesn't exist, you see, in the present state. So that's all. So we have finished. So what I have to do is analysis scenario, and go to here and batch run. Then select all the batch run. You see, it will run everything for you. It will run everything for you. So now, I mean, we are telling the computer to run all the three scenarios, so that it's preparing all the three scenarios. So we have some errors, but which is not a major error. So you can see errors. You see, these are just informations for a supercritical. So transition is occurring to this period. You see, from high velocity to say supercritical is when the fraud number is greater than, you see, 1, and subcritical is less than 1. It means the flow is changing from supercritical to subcritical. It means I can show. It means, you see, the flow is just like okay. Let me clear this. So this is the flow is changing from like this. You see, if the flow is coming like this, and it's changing into this. You see, or let me put it like this. The flow is coming like this, and you see, that's one. So the flow number, you see, which is greater than front number is velocity over or velocity. Let me check that. Under radical, the depth of water times G. That's front number. So when the front number is greater than 1, it is supercritical flow. When F is less than 1, it is subcritical flow. And when F is equal to 1, it means, when F is equal to 1, it means critical flow. That's hydraulics. So that means that is just simply an information given, so that if we have to check, we have to check and see, redo it if it is necessary. But the model or the hydraulic calculations can run, you see, can be computed without any problem. You see, no errors was encountered, and we can validate now. You see, no validation issue found, no problem. So you can compute now. Everything is computed. You see, now the results, simulation result in a graph. You see, you can create line. You see, click here, line. You can pick points. You see, like this one, 1, 2, 3. Then you can see the graphs. You see, let me decrease. Okay, for 10 years and 5 years. So just, you see, this is hydraulic grade lines elevations. As for 10 years, you see, as for 5 years. Something I have forgotten is global. Yes, we have to check here. Something has to be placed. You see, I placed the duration. The maximum storm intensity is 40 for 5 years, and for 10 years it is like, for 10 years it is 51. But just we are calculating, we are running the model now for a duration of 0.11, so 10 minutes. So we have to check this one always, otherwise it will not run. That's all. That's the result, you see. And if you want to see live, you see the profile, you just click here, select a drawing from here. You see, from the drawing profiles, you see it's to the outlet. Now open profile. You see, this is the profile. You can see the profile from, you see, the whole day. You see it. You see the hydraulic red line increased momentarily. You see, especially in in this 1.5, when you see, okay. Station, station, which station? Oh, it is in time 1.5, and maybe it's a 24-hour calculation. See, it's just show us the water flow in a 24 hours. So if we just leave it to continue like this, it will show us see the, the condition of flow in a different time intervals during the day. You see, so this is CivilStorm. You see, this is the result of the simulation. So that's all. That's all. The only thing which we add in the future state is just click here table here. We have to inform this thing, the nodes. You see, let me change because it is already changed. You see here 3 catchments already changed into village. So just click here, Control V, finished. And also there is an additional flow, fixed flow in this one is, see, we need to yeah, that's just, I should have written this one. See, yes, okay. Then the other is okay. See, we have some fixed flow here, as 6 fixed flow here, like here. You see, we have to add fixed flow, and also we have to add here hydrograph load, dry period hydrograph loads. So just come here, journal, copy here, copy. Okay, here, okay, here, fixed hydrograph load, click, select all, then control paste, control V, and this one is 0.2 for the 6, the bottom version or catchment 6. It's 2, I think. And also the same for here, also increased to 2 fixed. You see, this one also increased because the population is increased, and also the number 11 also changed into 2. Let me pick this one. Number 11 here is also, you can pick. See, flow here also 2. So you see that. So what's to catchment 11? This is 6. Slide selection. This is 3. The same. You see, let me not forget to put here. This is check hydrograph. Okay, see the same hydrograph everywhere. Dry period hydrograph discharge from the village. So that's it. We have to run scenario the same here. Batch run, select all, batch run. See, same thing. see, it's only some information um, has to be changed running for the future scenario. Okay, completed. See, yeah, the same. You see, there are some notification, but it doesn't have any problem. I think. Yes, no error were encountered. You see, the same thing. Compute hydrograph. You see, it's finished. Yes, detailed summary if you want. Report, catchment summary. See, if you want the report, it will generate for us detailed report. It's generating. So yes, that's it. She modified this in all this area. This is the data given. Flow, you see, time to peak, and volume of runoff, you see, here is very high in meter cube, especially in the channel, you see, central channel. You can see all the information here, and you can adjust, you see, how to print and so on, you see, and it's adjustable. And now we can see also the profile for this one. Check. You click here and choose some profiles like this one, then open profile. Here you will see that you see during the day, you see it's increased tremendously. I mean, you see, you can see the change in future. You see, it was not like this before. You see the water live. You see how it flows. We can see. You see, let us see again. You see, and also another legend and so on. And if we want to change charge options, you see how to print. If the colors, the data, the series, and so on, if you want to change, you can change them. See, so you can do, or you can study or investigate by yourself. This is the profile, and also you can see some graph. You see, like for example this one. Okay, you see, it's a graph. You see, for you see the difference graph. You see the base scenario hydraulic grade line for manual 10, and this is for manual 13. You see the red is manual 13, and 10 is manual 10, where we saw the high hydraulic elevation, hydraulic grade line. That is hydraulic grade line V square over 2G. So that's all. That's how we can calculate all our storm water discharge and design our system using CivilStorm V8i Bentley. Thank you for listening, and I hope I will come with Urban mic with the same data, and we'll see how to run the mic Urban as well. Merci beaucoup. Cheers.